Hi everyone, and welcome back. Ibrahim Siddiqui with you. Today, I'm going to show you how we can quantify the value, the extreme value of the cost of the cost range, which means um, how much high cost can be high and how much low cost can be low. And if we recall the curve that we started with in video 1 or 2. So when I was talking about the utility function, and we defined that the high cost is x0 plus h, and then we said that h is the payoff, which means this is the h, which means high minus x0, you get h. And so you have plus h and you have minus h, you get the low cost. And we said that h is the payoff here. Okay, so and then because before we did any computation or the equation that we derive for XCE, for example, or the utility function or the risk tolerance, what we have said, we need to set the cost, and we need to set also the utility between 0 to 1. And utility, we said this is the satisfaction. So I'm just reminding you what we have done in video 1 or 2, I believe. So today, based on what we learned from last video, we managed to uh, compute the overshoot, and we will use this important outcome that comes from the simulation that we have done last video, and we can use it. We can use this to compute the h. Once you compute h, you know the high cost and the low cost. Okay, so let's delete this and just give me a few seconds here. Okay, and also I need this graph. This is the response of a given budget. So we said, okay, so let's remove this. Okay, so for a given budget, let's say x0 equal 8,000, and this and someone give you also the fixed cost f0, which is 5,000, and v0 variable cost 3,000. So so 3 plus 5, 8, so which is 8,000. So when you plug this into the transfer function that we developed, blah, blah, and all the mathematical analytics, etc., that we have done last video, then you get this this response. So you get this response, which is the risk response or the distortion response. Okay, so and then we manage to compute the overshoot. So this is an overshoot. We managed to calculate the settling time duration there, the settling time here. And then we have rise time, which is the mobilization time, peak value, and so on. Okay, so these are the budget system performance metric, if I can say that. Okay, these are the performance metric that we managed to compute based on the budget, based on this given budget. Okay, so now I have overshoot. I have a value of overshoot equal 46.42. Remember that the overshoot is this one. Okay, so this is what we mean. So which means here is this maximum distortion. And then here is the steady state distortion. Steady state distortion is given. So in this case, it is 0.20. So this is the desired distortion. This is what the project team would like to have it. Okay. So we can achieve this, but we will achieve it at around 13 here, around 13 weeks. Okay. But we would like to know how much risk damping that this budget system has, how much angular risk velocity this budget system has. So we know the formulation. Okay, so we know to get this, and the mathematical expression is OS equal 100 time exponential minus pi and zeta, which is the risk damping over 1 minus zeta square. So when we substitute, first of all, we have to find the risk damping. So what is risk damping? So the risk damping is V0 to X0 time F0. So basically it's 3, 2 time 8 time 5. And this, if we do the math, so if we do the math here, we will find, so you have 40, you take the square root time 2, divide, not divide, inverse, time 3. So we get about 0, 2, 3, 7, 1, 7. So yeah, and if we plug this into this formula, so we say OS, overshoot, we take this, we time it by pi, and then there is a negative sign, and I divide, open pi, 1 minus 0.23717 square, and I have to take no, minus 0.23717 square plus and then exponential So I made a mistake here. I don't know. So basically, once you plug this, you get 46.42%. Okay, so we can also calculate the omega n, and we said it's f0, x0 over f0, this is squared, and then means that omega n is the square root of x0 over f0, which is x0 is 8 divided by 5, and then take the square root, 1 point equal 1.265. Also, we have omega n. We said this plus minus 1 plus squared. And then if you take 0.23717, take squared plus 1 square root plus 0.23717, 1 point, almost like 1.3, 1.3. So this is more precise, but it is the same. So we have 1.265. Okay. What else? Okay, so our goal is to find high cost and low cost. So which means I have to find H. All right. So when you look at the H here, when you look at this value, so which means it's a risk premium. It's the maximum risk premium. Okay, is the maximum that the delta X. So you can say here, this is a delta X basically, but is the maximum delta X allowed. Okay, because all of this curve is based on the risk tolerance. Right? So the risk tolerance dictate the shape of all of this curve, as you can see here, all of this curve. Okay, so basically H is the maximum value that is allowed. So basically it's the delta X maximum. And we know the expression of this delta X. So we know that delta X is X0 time distortion. But here I'm looking for the maximum delta X. Delta X maximum is what? Is X0 time epsilon this maximum distortion. And we know that the maximum distortion is this one. So if I want to express the what is the expression of this maximum distortion, so we know that overshoot equal what? Equal the maximum distortion minus steady state distortion over steady state distortion, right? So this is the desired distortion, and this is the maximum distortion. Where this maximum distortion comes from? It comes from the response of the budget system that was given to us. Okay, and then we said that we have to do something to reduce it or leave it, or I mean for risk mitigation. But let's get now the expression of the maximum distortion based on the overshoot. Okay, so we can rearrange, say, OS overshoot time steady state distortion equal maximum distortion minus steady state distortion. So, which means that the maximum distortion equal the steady state distortion time 1 plus overshoot. Okay, so if we can compute that since we know the steady state distortion and we know the overshoot. So maximum distortion, it's 0.2, which is this one, time 1 plus, what is the overshoot? It's 0.464, I think 42. So how much is going to be? So it's 1 plus 0.4642 time 0.2. It's a 0, it will be 0.28, I guess. Yeah, 0.28484. So this is the maximum distortion we get. Okay. So, and we said here that H is the maximum delta X. So we said H is the cost variation, the maximum cost variation. I hate to say variation, but we say this is a risk premium because variation in statistic has a different meaning than what we mean here. And this equal what? Equal x0 maximum distortion. So, and we know the x0, which is your budget, which is 8,000 time 0.28484. And if you do the math, then you will find time 8,000, your budget. So, which is 278.72 dollars. So this is the payoff or the maximum risk premium. So now, what is the high cost? So the high cost is x0 plus h, which is 8,000 plus 227.872, which equal plus 8,000. It's 10,278.72 dollars. So it means that the team cannot spend the maximum spending that they can make is 10,000. So if you go beyond that, then you have to go higher management to get approval. So the low cost equal x0 minus h. So minus 8,000 minus 8,000. So it will be 5,000. It says 8,000 plus 278.70. This is a minus, huh? So minus equal 5,007 to 1.28. This is the low cost. So which means in this, the utility, the function here, so this is the high cost and this is the low cost. Okay, so now we want to compute the risk tolerance. If you okay, before that, let's if I want to compute now XCE, so which means the forecasted cost or the actual cost, or you can say also the planned cost, since we are designing this, so we can evaluate the planned cost accurately. The basic formula we have is x0, 1 plus minus steady state distortion. So, which is 8,000 times 1 plus minus 0.2. And this will be, second here. So we have 1.2 times 8,000. So 9,600. So this will be your XCE. XCE, we said this value here. So here, okay. Okay, but I would like to know the risk tolerance for that. But in order to compute the risk tolerance, we need, based on the formulation that we developed in previous videos, we said that the risk tolerance is 2 beta H, which is also equal risk appetite sensitivity factor times delta X, which is C X0 distortion at the steady state. Okay, so so you can see now that I know H, but I don't know beta for the budget system, not for the historical. I will remind you based on the governing equation. So we said that this is the governing equation defined in the time domain. It is two risk capital, risk damping, risk frequency, and then the velocity plus omega n square distortion plus equal gamma omega n square, and then here for this it's a constant. This will be constant, so equal to this, or we can say this is u. We said it's a ut, and we choose that to be constant. So, but this gamma, if you remember, it's what? It's the risk appetite sensitivity factor historical over the risk appetite sensitivity for the budget system. So what we are looking for this. So which means that this is for the budget system that we are analyzing. So this, it comes from historical data, and this it comes from your budget, the budget that we are analyzing right now. Okay. So so now we have an issue here. How can we evaluate the systematic risk, the systematic systematic risk beta for the budget system, not for the historical, because this will be different, how you compute it and so on. Okay, so let's bring these two equation. So we have 2 beta h equal c x0 and steady state distortion. And we just now we evaluate the beta. So we said beta is x0 epsilon max. So it's x0 distortion, maximum distortion, and the psi x0 s. So we can simplify the x0. Okay, so what we get two. So we get 2 beta and 2 beta epsilon maximum equal C steady state distortion. And also we know the expression of the maximum distortion, which we just derive it based on the overshoot. Okay, so we have 2 beta, and then we have steady state distortion time 1 plus overshoot equal C and steady state distortion. We can simplify the steady state distortion. What we will get? We get 2 beta time 1 plus OS equal C. So we have an expression of the systematic risk and risk appetite sensitivity factor with overshoot. So there are two things that we don't know right now. We don't know beta and we don't know the risk appetite sensitivity factor. But remember that risk appetite sensitivity factor, we define it as 1 over logarithmic 1 plus square root of E beta over 2 minus 1 over 2 beta, which is also equal 1 logarithmic of cos hyperbolic 1 over 2 beta. So basically, the risk appetite sensitivity factor depends on beta. So we can rearrange. So we can write 2 beta 1 plus overshoot equal this expression 1 logarithmic 1 of this expression. It means the same. 1 plus E beta over 2 minus 1 2 beta. And let's rearrange and we do a separation of term. So one side beta, the other side the overshoot. So we will get beta time logarithmic of 1 plus beta E over 2 equal half of 2 plus overshoot over 1 plus overshoot. So we get this expression. Okay, now we have to solve. It is quite complicated. We have to solve for beta. But this is not a closed form equation, so which means it doesn't have an analytical solution. We have to solve it numerically through a program, through iteration. So which means you have to build a program with Python or with MATLAB or any preferable tools. So I developed a Python program here, and I can show you this. And this is the Python. So you call for yeah. So you call for NumPy and SciencePy optimize. You you look for this fsolve, and then you bring the warning if there is any errors. And then we have this function. I call it calculate beta. So the input will be your overshoot. So this overshoot that comes from your risk response, and then we calculate the equation of the beta, because here we define it here. So there is a left hand side and the right hand side. So the left hand side is, we said, is beta time logarithmic of 1 plus, you can say exponential of 1 over beta is the same thing, over 2. This is the left hand side. Okay, and the other side is half of 2 plus overshoot over 1 plus overshoot. So and then this one is a constant A, and we want to solve for beta. So that's why this is the equation of beta. And then we do the solution. So beta solution here, we use fsolve, and fsolve, I told you, it's coming from the SciencePy optimization here. And so we have the equation. We have you start, because this is iterative. It's a numerical solution here. So we guess we start with 0.1, and then we have a maximum iteration, and we set the maximum iteration to 1000, and then return the beta solution. Okay, if beta is positive, blah blah. If not, so this is just to capture if there is any error, because you remember that the risk appetite sensitivity factor was not defined when beta equal pure 0. So it's always, we said, plus or minus. Anyway, so this is a detail. And then if there is any error, then it gives you a message that there is an error. Then we go and calculate the psi, which is psi of the system, which is based on the beta. Once the beta is computed, then it will go into this formula. Okay, go to this formulation, and we define what is the, it's 1 over logarithmic of 1 plus over beta over 2 minus 1 to beta. Okay, and then we give our overshoot. So here, just giving your overshoot, we already computed based on the risk appetite sensitivity factor zeta, and we plug it into the formula of overshoot, which we said it's 100 times exponential minus pi over pi c 1 minus c zeta square. And we said also that zeta is your v0 to x0 f0. So we have all the ingredient to compute zeta, to compute the overshoot. Now we put the overshoot into the calculate beta OS. Where is calculate beta? Calculate beta here. So we put a definition here. It's a procedure. So so this number will come here and then do the calculation, the iteration, blah blah blah. Once it find the solution for beta, then we calculate epsi in another def, and we get the result here, return, and print it. So we call this calculate psi, and we get this result. So you can see here. So we get the value of beta and the value of the psi, okay, of the system, of this particular budget system. Okay, so now we have computed beta, and we said it is how much? 0, 0, 2, 3, 3, 2, 8, 8, and psi is 0.6831. Okay, so so I think now we have everything. So we managed to compute the systematic risk for the budget system and the psi for this particular budget system. Now, if I want to calculate gamma, which will be your historical, and the one that we just computed, which is this one. And you get the gamma, and you plug it here in this governing equation. And from here, you get your transfer function. And from this transfer function, you get something, etc. So for us, for this response, we were assuming that equal 1. So we are assuming this equal 1. It means that we assume that h equal s, but it could be a different value. Anyway, so now we have the previous formulation because we want to calculate the risk tolerance. So I know that the risk tolerance equal to beta h equal c x0 epsilon at steady state. And then we have everything, I guess. So which means risk tolerance if equal 2 times 0.233288 times h. We computed h. How much it was? 2278, 2278.72. 2278.72. So now we will be able to compute the risk tolerance. 2278.72 times 0.233288 times 2. So we get this risk tolerance 10631961. Okay, so and now if I want to calculate XCE, and then I told you that XCE it's this, I mean the easy way is x0 1 8000 etc. But also we can calculate using the formulation that we derive in video 2 or 3. And we said it is equal to risk tolerance time logarithmic of half exponential high cost divided by risk tolerance plus half exponential low cost divided by risk tolerance. So if you substitute the values of high cost, low cost, and the risk tolerance, you will get XCE almost exactly 960. You may find something more or less than this because of the how many digits you are taking after the decimal. But you will get roughly something like this. So which means if you have activity 1 and 2, 3, and so on, you can, based on this, you can say the plan value roughly, you will have very accurate plan value in terms of cost. And also in terms of duration, you do the same thing in terms of duration. So let's do it here. Because you know that we said that duration, it's minus logarithmic of delta over C omega n. So we know psi, we know omega n, and then if we assume this for 2%, then we get something 4 over this. And then we found the system tell us that is 13, the settling time. So the duration will settle, and then this we said this is the 2%, okay, which is delta, the band, the criterion. And we found it will settle in 13%. Now, if I take, which is 13 weeks. Now, if we say the buffer will be what? 13 delta D will be 13 weeks. The maximum, 13 weeks time the overshoot, I believe. If I think this one, the maximum, yeah, the maximum duration. So this is like the age, but in term of D, in term of duration. And this what is gonna give you. So we know the overshoot. Overshoot was I think 46 something, 46, 42. So this will be 13 times 0, 46, 42, about 6 weeks. So which means the maximum, the buffer will be plus minus 6 weeks. So you have a buffer here. So just by giving you this budget, just by giving you the the indirect costs and direct costs and the budget, of course, we managed to calculate all of this by using the governing equation and by using the control system theory. That's it for today, and next time we will talk about contingency and overshoot and other things. By the way, I have a lot of things to discover within this governing equation. This is just a basic elementary stuff that I'm showing you. Once we go to, if you have the data, then we can do really very sophisticated things. We can use Fourier, we can use, I mean, reading, we can rebuild your governing equation from your own data. Keep in mind that this governing equation is analytical equation. What if you build it from your data? So it will be really amazing. Thank you very much, and please don't hesitate to hit the button like and subscribe if you didn't do so. Talk to you soon. Bye.